In this video, we are going to go through the new standard mathematics formula sheet that you're going to get with your exams, just so you can sort of get an idea of what's on it, because there's not a lot of headings. There's some formulas and things, but it doesn't really tell you what that formula is for. So you're going to have to know some of these. So let's work our way through. We're going to start up here with the measurement section. Precision is just simply the term that we've used that you might remember us using is actually the limit of reading. In other words, that's the smallest unit of measurement or accuracy. You might say, look, you could measure something, for example, if the limit of reading was 1 centimeter. We could measure with the measuring tape we were using, the closest we could get was 1 centimeter in accuracy. Then we'd say the absolute error is plus or minus half of that limit of reading. In this case, half a centimeter. Okay. The upper bound, so if I use this same example, so let's say I measured something at 10 centimeters using the same limit of reading from our example up here, then I'd say the upper bound is the 10 centimeters plus the absolute error. The lower bound would be the 10 centimeters minus the absolute error. So I've got an upper bound and a lower bound. All right, that's measurement. What else have we got? We've got a heap of length area, surface area, and volume formulas. Let's go through and explain what each one is so that you know which one to use in your exam. This first one, L, is the length of an arc. Now, an arc is just a section around the circumference of a circle. The things in here that we need to know, this theta symbol and the R represent the theta is the angle that is made by the two lines forming the pointing towards the edges of the arc, and then R is the radius. So if I know the radius, the angle, I can work out the length of the arc. A, this is an area formula, equals the area of a sector. Now a sector is the piece of pie made by this arc and the two radii. It's the space inside that sector or that piece of pie. Similarly, it's the same value for theta. So if I've got the angle at the center of the sector and I've got the radius, I can plug them in to work out the area of the sector. Here's another area formula. This is for the area of a trapezium. Okay, a trapezium is this kind of shape. It's got two parallel lines, but they may be of different lengths. And we need an H, an X, and a Y. X and a Y are the lengths of the two parallel sections, and H is the vertical distance between them. So if you know those, you can plug it in. That leads on to something very similar. This next one looks similar. You'll see this little squiggly equals sign. This means approximately, because this is what we're going to use for our trapezoidal rule. This is where we use trapezium, or a trapezium, to work out. Let's just see if we can back that up one. Because I've got a shape here that doesn't have a straight edge. It's kind of like got a curved edge, so I can't get it exactly. Hence the approximate sign here. But if I make a trapezium in there that approximates this shape, then I can apply this rule to it. My DF and my DL stand for the distance of the first side, the distance of the last side, and the H is the distance between them. Okay, and I can just plug those in. Now, you might be asked to use the trapezoidal rule more than once, so you're just going to repeat that process for each strip or each column. Next one is another area formula. This is a surface area, and it relates to the surface area of a cylinder. I need a radius value, and I need an H value. H is the height of the cylinder. R is the radius formed by the circle at the top. Now, one thing to watch out for with these is whether or not the cylinder is what we call closed. That means it's got a lid at the top and bottom, so the surface area counts the circular pieces on both sides. Or if it's open, we scratch this part out. We don't need it. If it was like a pipe, for example, then we call that an open cylinder, and the surface area is just this piece. This one is the surface area of a sphere. All we need to know is the radius. This one, volume equals a third AH. It's the volume of a pyramid or a cone, where A is the area of the face, say on the bottom of the cone or the bottom of the pyramid, and H is the height of it. And lastly, the volume of a sphere is 4/3 pi times the radius cubed. That's it. Wow, there's a bit there. That's the area and volume formulas. What else do we have on here? Some trigonometry formulas. This one is for the area of a non-right angled triangle. If it was a right angled triangle, then you're just going to use half times base times height. So something like this, for example, where I've got two sides and the angle between them, I can work out the area of that non-right angle triangle by applying this formula. This could be my A, this could be my B, and this would be my sine C. I've got the sine rule, which I use to find unknown sides or lengths of a non-right angled triangle. And these two are both representations of the cosine rule. The first one is written in a format where I'm trying to find an unknown side, and the second one is written in a format where I'm trying to find an unknown angle. Okay, so the cosine rule, look, often it depends how you memorize it. For me, I always try to apply the sine rule first. If I can't make it fit, then I'll have a go at the cosine rule. What else do we have in our tour of this formula sheet? Some financial maths. This is our future value formula. So if we're taking the future value, it's the same thing basically as the compound interest formula, but instead of an amount and a principal, we've got a future value and a present value. FV is our future value, what the amount will be worth in the future. PV is the present value. R is our interest rate, but remember that has to be written as a decimal. You can't use the percentage value. So if it was 8%, you'd divide it by 100 to get 0.08. That's the decimal that you would use. And then N stands for the number of time periods. Depreciation, which is the decrease in value of an asset, let's say a car. There's two types. Straight line is just where it goes down by the same amount every year. So in this case, our letters stand for S is the salvage value. In other words, what's it worth after it's been depreciated. VO is the value at its original state when it started, so the original value. D is the amount that it's depreciating per period, and N is the number of time periods. Another type of depreciation is the declining balance, and you'll notice if you have a look, you might see some similarities between the future value formula and this, except that we've got a minus in here instead of a plus because the value is coming down rather than going up. The S and the V are exactly the same, the salvage value or the original value. And just like in our future value formula, the R and the N represent the interest rate or the rate of depreciation. Sorry, I should have changed that. It's not an interest rate, it's the depreciation rate. So I was lazy, sorry. But N is still the number of time periods. We're nearly done. Now, statistical analysis. The formula here at the top. Actually, let's do the outliers first. Outliers are scores that are maybe really low or really high, that they're sort of way off the rest of the data. To tell if something is an outlier, we apply this test to it. If it's less than this or more than this. Now, what do all these pieces mean? Q1 is our median of the bottom half. So to find Q1, we would find the median of our data set first of all. That's the middle, the median. And then we'd take that bottom half and we'd do the median of that. That gives us Q1. It's our first quartile. Q3 is the median of the top half. So the same thing, but this time done on the top half of the data. And the IQR stands for our interquartile range. Now that is just simply the distance between Q3 and Q1. So you can take Q3, take away Q1, will give you your interquartile range. And you could apply that test then to see if a value sits higher or lower than those guidelines to identify them as outliers. Z-scores are tied in with this graph down here of normal distribution. This is the formula for calculating a Z-score. And all we need to know is we will be given an x value, which represents our score in the question, whatever it is. We'll be given, you'll probably be given a mean or the average, and S is the standard deviation. You can apply those in. Sometimes you might be given the z-score and asked to calculate, say, the standard deviation. So you're just going to put in the things that you do know and solve for the unknown after that. But most of the time it'll be calculate a z-score when you're given these pieces of information. Nearly done. The normal distribution, this curve, these numbers along the bottom here are z-scores, and they help us identify the amount or the percentage of data that sits within certain z-scores. Between a z-score of -1 and 1, you have, in a normal distribution, 68% of your scores. So I've got between here and here, that would represent 68% of the data. Going out, approximately 95% of scores sit between -2 and 2. So for that whole piece there, from there to equal 95, these two pieces must equal 13.5 each. And then finally, the little extra bits here between z-scores 2 and 3, or -2 and -3, they each represent 2.35. What that means, I guess, is also in the middle here, you've got two lots of 34 for this to equal 68. Above the middle here will be 34 plus 13.5 plus 2.35. And I think that's it. That's your guided tour of the NESA formula sheet.